All right, so for the next few lectures, we're going to be focusing specifically on solutions. And a solution, I think we've heard this word many times. We're going to talk about what it is today. We're also going to talk about how solutions form, and that's pretty much going to be the bulk of today's material. We might be able to review molarity, but it'll just depend on how things go. Okay, so let's review water. Okay, water, let's talk about it. It's a very polar substance, right? We've already established that when we did molecular geometry. We learned that it was bent. There are two lone pairs on the oxygen atom in the center, right? Which means that there's a very high concentration of electrons on the oxygen, low concentration of electrons on the hydrogens. So we say that the oxygen has a partial negative charge, and the two hydrogens have partial positive charges, right? Water is capable of hydrogen bonding because of its OH groups, and it's got many unique properties as a result of that. So this is something that we already established. The reason why we're reviewing water is because today we're going to be talking about solutions involving water. So we need to know what kind of creature we're dealing with so that we can discuss its properties. Do we agree on all these features about water? Yes, yes, polar, bent, capable of hydrogen bonding, lots of unique properties. Okay, so a solution is just a homogeneous mixture, right? It's two substances physically mixed, and they are in equal proportions. In other words, it's uniform throughout is a better way to put it, not equal proportions. Equal proportions implies that 50% one, 50% other. And that's not really true, okay? Homogeneous means it's uniform throughout. Uniform throughout. Composition is uniform throughout. And so the solvent is the substance that is present in the greatest abundance. In other words, it's what you're dissolving in, right? And then everything else will be a solute. A solute is something that's being dissolved. Okay, so the solute is what's being dissolved. The solvent is what you're dissolving in. Now, if you're dissolving a liquid in a liquid, that's fine. You can still have a solute and a solvent. Okay, it doesn't have to be a solid dissolving in a liquid. It can be a liquid dissolving in a liquid or a gas dissolving in a liquid. And the solvent is present in the greatest abundance. That's what you're doing the dissolving in. And the solute is what's being dissolved. Okay? Solute plus solvent makes a solution. Those are the two components of a solution. And again, a solution has a uniform composition throughout. If you make some sports drink, right? You take the powder, you dissolve it in your water, you mix it. That would be a solution, right? The composition would be equal throughout. And it should taste the same at the top, at the middle, and at the bottom. Any questions on this vocab? Okay, now in an aqueous solution, that just means water is the solvent. Okay, think back to lab yesterday. If water is the solvent here, what do you think is the solute based on this color? What do you think the solute would be? What do we see in lab that's this shade of blue? Copper 1 or copper 2? Copper 2 is blue, right? Copper 2 is blue. So water is the solvent in an aqueous solution. And those are the solutions we're going to be looking at primarily today, okay? We're going to be looking primarily at aqueous solutions and whether or not something will dissolve in water. So here are two words we need to talk about. If a solute dissolves in a solvent, then that means it's soluble. Okay, the word we use to describe it is soluble. If a solute dissolves, then we say that it is soluble. And what does dissolve mean? Well, dissolve means forms a homogeneous mixture. Okay, so dissolving just means forming homogeneous mixture. If I take my sports drink mix and I dump it in water and I stir, 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 and all my sports drinks powder is gone, and now I've got a homogeneous solution, that's dissolving, right? Dissolving just means forming a homogeneous solution. So if a solute dissolves, then we say that it is soluble. And if a solute does not dissolve, then we say that it is insoluble. Insolubility for ionic salts is on a continuum, which we will discuss in great detail next semester in Chem 2. But right now we're looking at it just yes or no. The reality is the answer is yes for everybody. It's just some dissolve better to a greater extent. But we'll look at that extent next semester. Right now we're going to make it pretty much black and white. Next semester we'll get into the gray. So if a solute forms a homogeneous solution, in other words, then we say that it is soluble, and if it is not, then it is insoluble, right? So something that is insoluble would just sit on the bottom of your beaker, right? You put it in, you stir, 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 nothing happens. It's just sitting there on the bottom, right? That's not a homogeneous solution. That's just something sunk on the bottom of your beaker. And solubility comes directly from intermolecular forces, okay? Why do I have something that dissolves in one thing and not in another thing? It's because of intermolecular forces. Okay, the IMFs of the solute must match the IMFs of the solvent. Okay, that's the requirement. If the solute and the solvent do not have IMFs that are compatible with each other, then there's not going to be solution formation. Okay, you're not going to get a homogeneous mixture. You're going to get layers. We're going to have one sink to the bottom, which I guess is also layers. There are a few limitations. Again, we'll get into those next semester. Right now, it's pretty much black or white. Next semester in Chem 2, we'll deal with the gray. But as a rule, generally speaking, the IMFs of the solute need to match those of the solvent, because if they don't, you're not going to have a solution. Remember, a solution is a homogeneous mixture, right? And for that process to occur, the intermolecular forces of the solute and the solvent need to be compatible. Otherwise, it's not going to happen. Everybody cool on this? So we're going to do a little bit of reviewing of intermolecular forces today so that we can have the groundwork for talking about solution formation. Okay, so we're going to look at ion dipole, hydrogen bonding, and London forces with regard to solubility. We're going to look at each one of those individually. Solutions that are formed based on ion dipole, solutions that are formed based on hydrogen bonding, and solutions that are formed based on London forces. Okay, they have to directly match. There is a little bit of a gray area, but we're not going to look at that this semester. We'll look at that next semester. All right, so let's look at first ion dipole and its solubility rules, okay? Ion dipole. Let's remind ourselves what this intermolecular force looks like. It occurs between an ion, right, Na plus, Mg plus 2, K plus, right? And the dipole we're specifically referring to here is, who remembers? Oh, I'm so thirsty. I need some water, right? So the ion we're referring to is any cation or anion. The dipole we're referring to specifically is water, okay? So when a salt dissolves in water, that is the result of the ion dipole intermolecular force. Okay, so if I take my chunk of salt, remember a salt is not a single cation and a single anion, right? That's not how it exists. When you look at your table salt tonight and you're analyzing it with your eyes, you're not seeing a single cation and a single anion. You're seeing a repeating crystal lattice, right? Cation, anion, cation, anion, cation, anion, repeating around in this regular repeating arrangement we call a crystal lattice. So if you take that salt chunk and you chunk it into your water and you stir, 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 right? This cation and this anion and all the other cations and anions completely separate from each other, and water surrounds each one of them. Do you remember seeing this when we talked about intermolecular forces? Yes? So the partial positive of the water is attracted to anions, right? So that's why the hydrogens are all facing in here. And the partial negative region is attracted to the cation. That's why all the oxygens are facing in here. Now this is what it looked like initially, but by the time the solution is all formed, it will look like this completely all throughout, okay? And so that process we call is solvate. So this cation completely being surrounded by water, that's called solvation. And the process of a salt breaking into its ions is called dissociation. Okay, so those are two vocab words. I've got a quick little video just to show you this. Hope this link still works. It's an old link. Let's see if it works. Oh, yeah. There we go. So there's our salt. We're dumping it into water. We're giving it a good stir. All right, now let's zoom in and see what's going on. So there's our crystal, and each anion and cation are being completely surrounded by water. Now this is a very simplified model, okay? It's not going to happen at one little corner and then spread throughout. It's going to happen simultaneously on the entire crystal at once. Okay, so imagine what's happening here, happening everywhere. It's like taking a chunk of meat and just throwing it into piranha tank, right? It just gets completely ripped apart. Okay, that's what's happening all across the entire crystal. Each cation is being surrounded by water, each anion is completely surrounded by water. And when it's done, you've got cations with water surrounding them, anions with water surrounding them. That's what the entire solution looks like. That is the quintessential ion dipole intermolecular force. So when you're done, the whole thing looks like this, right? All of this is gone. There's no more crystal. The entire thing looks like this. Now again, next semester, we'll deal with the situation of, does it completely dissolve? Does it completely dissociate? Or does it incompletely dissociate? That's an equilibrium calculation, okay? Right now, we're just looking at black and white. We're not dealing with the gray. And again, the reason that we get dissociation in a salt is ion dipole intermolecular forces. That's what's the driving factor here. So let's talk about some vocab. What does water soluble mean? If we're breaking this sentence, a water soluble salt dissociates when it is hydrated. What does water soluble mean? Dissolves in water, right? What does dissociate mean? Right, it breaks into its ions. And what does hydrated mean? Hydrated and solvated are the same thing. It is surrounded by water molecules, right? So if we replace the words that we just learned, salt that is able to dissolve in water breaks apart into its ions when those ions are surrounded by water molecules. All right, now let's look at the solutions that are the result of hydrogen bonding in soluble and water. Right, so we're looking at solutions that deal with hydrogen bonding as the driving force. The solutions we looked at just a second ago were all driven by ion dipole. Now let's look at some solutions that are driven by hydrogen bonding. Okay, so again, let's review. Hydrogen bonding occurs when we have OH, NH, and FH bonds, right? FH is going to be kind of weak. We're not going to really be dealing with too many FH bonds in this class. We're going to be dealing with a lot of NH and OH, okay? So the ones that you're going to be seeing most commonly are alcohols. Alcohols contain an OH group, and amines. Amines contain either an NH or an NH2, depending on the amine. So for instance, here's an alcohol, right? This is carbon with 2 hydrogens bonded to a carbon with 3 hydrogens. But this right here is the OH, right? So you're more familiar probably with seeing it like this, like CH3, CH2OH. When you take organic chemistry, you'll learn this notation. There's just shorthand. Okay, so you see the stick that just represents carbon, carbon with their hydrogens, and then that's the OH sticking down. Okay, so alcohols with chain length of 6 or less are soluble in water, and that would apply to amines too. Okay, so OHs and NHs. So the reason why I say 6 or less is because once the chain length gets beyond 6, something interesting happens. But so long as the hydrocarbon portion of the chain is 6 or less, hydrogen bonding is a pretty significant intermolecular force. Okay? And so the hydrogen bonding effect is greater than the London forces effect here. Okay? So for instance, if you've got this molecule, you're looking at what is it IMFs? This part's London forces, right? This part's hydrogen bonding. So long as the chain is 6 or less, this is the predominant IMF. But when this chain gets too long, now the chain's London forces have a greater influence and have a greater impact on solubility. But so long as it's 6 or less, it'll dissolve in water. All right, so there's cartoon representation, right? There's the OH part, the hydrogen bonding is occurring with water. Hydrogen bonding is not occurring with the carbons and the hydrogens, right? Because this piece down here is nonpolar. So this is nonpolar, London forces only. London forces are incompatible with hydrogen bonding. Does everybody see why I say 6 or less? Okay, because when this chain gets to be too long, and this chain's way, way, way long, now you've got a pretty significant influence from all that nonpolar component that actually overrides the effect of the hydrogen bonding. So I'll show you some more pictures. So alcohols are insoluble in nonpolar substances because their intermolecular forces wouldn't match. So for instance, if I gave you an alcohol and I asked you if it was soluble in decane, I wouldn't say ethane because ethane's a gas at room temperature. Let's just pretend a big long chain. Right? An alcohol would not be soluble in that. Their IMFs don't match. This is what happens if the chain gets to be too long. Okay, you've probably seen this in your biology classes. If you take one decanol, okay, so that's a 10 carbon chain, and then there's an OH on the end, right? So that 10 carbon chain is capable of some pretty serious London dispersion forces, right? Just sketch it out real quick. If you've got a marker that works, if you've got a 10 carbon chain, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, just imagine hydrogens all here. Okay, this piece is London forces, right? This piece is the hydrogen bonding piece. Once that chain hits about 6, that's kind of the magic number. Once that chain is greater than 6, now the London forces are the primary influence on solubility. And they take over in terms of who's the more predominant intermolecular force. London forces become the significant influence. And it overrides the hydrogen bonding. Okay? So what happens is if you take decanol, one decanol, and you throw it in some water, you can shake it all you want. And what you'll get immediately, it might look for a few seconds like it dissolved, when in fact, what you did is you formed the micelles. Do you remember this from biology? This also happens when you have a salad dressing with oil and a water part, right? You shake up the salad dressing. It looks like it's dissolved for a few minutes. You can pour it around. But then it separates back out. Right? So immediately you'll get these micelles. The nonpolar components are all facing in, and the OH part's sticking out. Right? And so the OH is happy to be in the presence of water. We say that it is hydrophilic. Right? And then this part is the hydrophobic part. It's all on the inside. So you have all the nonpolar facing in, all the polar facing out. And then eventually, if you let that sit, it'll just separate out in layers. You'll have all the nonpolar in one place, all the polar in the other place. Does this make sense? Yes, yes, yes. I've got a little video I'm going to show you about this. It is on the YouTube channel. So you can see it for yourself if you go, it's in the lab videos. And we want intermolecular forces and solubility.
This video is going to demonstrate the effect of intermolecular forces on physical properties. So first we have a nonpolar solvent. This solvent is capable of only London dispersion forces. That means that it's going to be incompatible with a solvent that is polar. Polar solvent that we'll be using, we have two. We have water on the left, and we have ethanol on the right. Both of these solvents are polar. They're capable of hydrogen bonding. So when I combine a polar solvent capable of hydrogen bonding with a nonpolar solvent that is not capable of hydrogen bonding, I will see layers form. And to demonstrate this, we've got some water. We'll add to our nonpolar solvent. And we'll also add our ethanol to our nonpolar solvent. In both cases, we see the formation of layers.
Couldn't find the camera.
Here we go. In both cases, we see the formation of layers. Right? This shows that the polar solvent and the nonpolar solvent are immiscible in each other. There's ethanol, there's water and our nonpolar solvent, and there's ethanol and our nonpolar solvent. We see formation of layers. This indicates that the two are incompatible with each other. However, when I add my polar solvent to another polar solvent, say I add ethanol to water, then we do not see the formation of layers. So when I do ethanol in water, there's my water that I'm pouring in. Ethanol is already in the test tube. There are no layers that form. They are completely miscible in each other. Solubility is a function of intermolecular forces. If the solubility, if you see formation of layers, that means they are insoluble in each other. And if you do not see formation of layers, that means that they are soluble in each other. If the intermolecular forces are incompatible, then the two liquids will not be soluble in each other.
All right. So I feel like that's a little bit easier for me to show to the whole class just because I can make it on the big screen. Now again, that solubility is conditional, right? If that chain length is 6 or greater, then the effect of those blended forces now is the predominant factor. You're not going to have solubility. Now when we dissolve a sugar, okay, a sugar is a molecule that contains lots of OHs. So next semester, if you take Chem 1124, the elementary or biochem class, we'll spend a lot of time talking about sugars. So molecules that contain lots of OHs, these are all OH groups. This is a sugar molecule. Sugar is able to dissolve in water if it has lots of OHs, because those OH groups are able to hydrogen bond with the water. Okay, so this does not dissociate though. That's really important. You're not going to break up into ions because there are no ions to make. Okay, so this dissolves, but it doesn't dissociate. That's an important distinction. Okay, you're not going to get those ions. There's no ion dipole IMF because this is not a salt. This is a sugar. So the water is hydrogen bonding with those OHs. I'm trying to put it in like a cartoon form there. Okay, so the sugar actually stays intact. Okay, the entire sugar molecule remains intact. It is just hydrogen bonding with the solvent. Okay, so don't think about it as being ripped to shreds like with the salt, right? With the salt, it got ripped to shreds. But that's not happening here. Okay, the sugar is actually staying intact. All right, let's talk about a carbonyl. Remember a carbonyl? A carbonyl is a C double bond to an O. Remember that? We talked about them specifically when we were discussing intermolecular forces. I said carbonyls are important because the carbon has a partial positive and the oxygen has a partial negative. There are two lone pairs here, so the carbon's partial positive, partial negative. Okay, so a carbonyl is capable of hydrogen bonding with water. It's not capable of hydrogen bonding with itself. Okay, a carbonyl can have dipole with itself. But if you put a carbonyl in water, again, assuming that that chain length isn't too long, it can hydrogen bond with water. So if I give you a carbonyl, right, an aldehyde or a ketone, so you don't need to worry about distinguishing those right now. If I give you a molecule and you see a carbonyl, so long as the chain that it's part of is not too long, it can hydrogen bond with water. Okay, it won't hydrogen bond with itself. It'll have dipole with itself. But it'll be able to have hydrogen bonding with water because of that partial positive, partial negative situation here. Does this make sense? This makes sense. Again, it's going to be conditional based on chain length. And now a carboxylic acid is the next scenario we look at. A carboxylic acid is CO2H. What does that look like in terms of the Lewis structure? know this is kind of a busy screen right now, so I'm trying to find a spot to write. It'll show up okay. All right, so CO2H looks like this. C double bond O, OH. And then there's the rest of the chain, right? So whatever that chain is. Okay, so this is called a carboxylic acid. Okay? So this is going to be a special case as well, because now you've got the hydrogen bonding of the OH plus the polarity of the carbonyl. As a net, that's going to be pretty polar. But again, it has to be a small chain. The chain magic number is about 6. Once you get to 6, beyond that, the London forces component overtakes the polarity component. And so when you study organic chemistry, you'll call these fatty acids. So if the chain is really long on a carboxylic acid, that's called a fatty acid. So next semester, if you take elementary organic, or if you go on to take organic 1, we'll study those in great detail, right? So when that chain gets really long, that's called a fatty acid. This piece right here is the polar component. This piece is the nonpolar. And when that chain gets to be too long, the nonpolar component predominates and makes the primary, it becomes the primary influence on solubility. So just like with the alcohols one I showed you a minute ago, right? If the chain becomes too long, it's now insoluble. So you'll get layers. You'll separate out into layers. Or if you shake it up, right, it'll be in these little micelles, which will then separate out into layers. All right, now the last one would be solutions based on London forces. Solutions based on London forces. So are these going to be solutions that involve polar or nonpolar substances? It would be what? Well, for London forces, it would be nonpolar, right? London forces are all solutions that are nonpolar. So if you are nonpolar, you are only going to dissolve in nonpolar solvents. Water is extremely polar, right? So you would not expect something nonpolar like a hydrocarbon to dissolve in water, right? So this is 1, 2, 3, 4, 5. That's pentane, 5-carbon chain. It would not dissolve in water, right? This is nonpolar, has London forces only. So you would not expect it to dissolve in water, but you would expect it to dissolve in other nonpolar substances, right? Because the IMFs match. If you dissolve, let's say, pentane in decane, that's a 10-carbon chain, both of those only have London forces. So London, that matches, that will dissolve. So the IMFs must match in order to have solubility. And if they don't, no solution, right? Literally, no solution. They just get layers. Okay, so looking at this molecule, let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's nonane. What kind of substance would this be soluble in? Water? No, it would not be soluble in water, right? It would be soluble in something nonpolar. Any molecule that's composed of carbons and hydrogens. And by the way, those carbons and hydrogens could be linked up in a ring, right? It could be a circle, like a cyclic molecule. So for instance, if instead of being a CH3 here and a CH3 there, they were linked together and this was a ring, that's still a nonpolar substance. So nonpolar dissolves in nonpolar. You probably learned it in high school, like dissolves like. Do you remember hearing that in previous classes, like dissolves like? So if the IMFs match of the solute and the solvent, you're good to go. If they don't match, not good. And just a reminder that only salts dissociate. Remember, dissociate means produce ions. Only salts are going to dissociate. Other substances might dissolve, but they will not dissociate. Okay, so if you dissolve a carbonyl compound in water, it might dissolve, but it's not dissociating. Okay, you're not breaking it up into ions. So make sure that you note that. Only salts dissociate. Now, this is a vocab word you may have heard before, electrolyte and non-electrolyte. It just means conducts electricity. Okay, so an electrolyte, electrolytic solution is able to conduct electricity because the ions are what do the conducting. Okay, when you dissolve a salt in water, you get ions. Those ions, because of their positive and negative charges, are capable of conducting electricity. So you get an electric current. All right, this is why you don't go swimming during a lightning storm, because the water you're swimming in is not pure H2O. Water itself is a horrible conductor. Right? But water with salt dissolved in it is a fantastic conductor. It's not the water that's doing the conducting, it's the salt. Okay, so that's why you don't take a shower with your toaster either, right? Because those ions in the water are great conductors. They are electrolytic. Yeah?
So why is it like sports drinks advertise having electrolytes?
Because of the salt component, you know, salt that's lost through sweat. So I don't think that's like athletes care about whether or not it conducts electricity. I think to the mass media, that sounds like a cool scientific word, but all they're saying is that it contains salt. Yep. Now, a non-electrolyte would be a substance that doesn't conduct electricity. It might dissolve, but it's not going to do any conducting. Right? If you dissolve sugar in water and you put your light bulb in it, the light bulb's not going to go off. This is an experiment that I do with the kids when I go out to the schools. There's actually a video in the teachers section of the YouTube channel on it if you want to see it. I take the light bulb, I stick it in a solution of salt, light bulb gets bright, right? Stick it in a solution of sugar water, nothing happens. The sugar might dissolve, but because it doesn't dissociate, it can't conduct electricity, okay? Not going to conduct. So just because sugar dissolves doesn't mean it's going to be an electrolyte. Electrolytes are substances that are ionic. Okay? The ions are what do the conducting. So there would be an electrolyte, right? Notice you've got cation surrounded by water and anion surrounded by water. It's those cations and anions that do the conducting, not the water itself. Okay, so I think actually what we're going to do is we're going to stop right here because I've got something here in class that I want you to do. So we're going to stop right here for today in the lecture portion. So